was given by Professor Naoufel Salhi. He is from Tunisia, and he will talk about local times of Gaussian processes. Yeah. So he will try to explain everything for you. So, but if you don't understand something, please let us know, and we will explain you. Yes, and maybe you will have some programs after lecture, and you can come tomorrow, ask questions, and we will discuss. Okay, so please.
So thank you very much for the introduction. As you exactly said, it is the first lecture is about local time of a specific family of Gaussian processes followed by Gaussian integrators. I will try in this lecture to introduce this concept of local time. And I will try to give even some technical details, not so complicated techniques, so that you may even understand what we exactly do in this field. I will go straight to the problem. So let us consider a curve f function 0, 1. And we will define the following measure. Okay, so it is a measure in RT, and it is defined as follows. So if we take the Borel success from RT that we denote the measure of this set. So if we take some set that way. What is the measure of the set here? Lambda is here the Lebesgue measure. Okay, so we compute the times t here, such that f of t belongs to this set. So we look to this part of the curve, and we take its pre-image by f. What are the t that corresponds to this part from the curve, and we compute the Lebesgue measure of this times t. So that's why it is called occupation measure, because we compute how much time the curve spans at this set t. So occupation measure, or also visitation measure. How much lasts a visit of the curve to the set. Of course, we do this to every Borel subset D from maybe a first remark is that this is a positive, well-defined measure, and even it's we can compute the measure of the whole space. How much time spent in the whole space? It is the whole set of time. So it is one. It is even a probability measure in R. So what we will focus on is the following. If this measure has a density, we have measures that are discrete, we have measures that have density with respect to the big measure, and we have measures that they are neither discrete nor absolutely continuous with respect. So if this density, if this measure has density with respect to the Lebesgue measure in IT, then this density is called by the local time of the curve. What is the local time? If it exists, it is maybe you can demonstrate du with respect to d lambda, the Lebesgue measure in R. Okay? The radon nicotine derivative. This is just a symbolic notation of the density. Okay? So if this measure has a density, we call this density the local time. Well, so the definition is simple, and we will have some first property that we can easily obtain from this density. Okay. Now imagine that the set D does not intersect the curve. Means that if we take a set D, this time, of course the curve spans 0 time here. Okay? So in this case, the measure, let's say D prime, this is 0. And so what we can understand, whenever you take a set that does not touch the image of the curve, the measure is 0. So the measure is supported by the curve. The support of the measure is the curve itself. It lives here. It lives on this, the image of the curve. Okay. Okay. Now we have an idea about the support of the measure. We can ask the following question. Is there a situation where, if we know the support, we can say that the density exists or not? Yes. In fact, we have the following small exercises. Yeah. Okay. If f was continuously differentiated, okay, and the dimension here is greater or equal than 2, then the Lebesgue measure of this curve would be 0. Okay. The Lebesgue measure of this is okay. I will come back to prove this small result after. Okay. Let me continue on my ideas. Okay. Now, the support in this case, this curve in this case has Lebesgue measure 0. In such case, the occupation measure, which is supported by this curve, cannot have a density. The density cannot exist on a set which has a Lebesgue measure 0. This cannot happen. This is the second small exercise. Okay. So if we have a non-zero measure such that the support is a null set RT, maybe a discrete set of points, for example, or a segment line, for example, in R2, R3, then the measure cannot have a density. So let us combine these two ideas and see what we do. So if the curve is continuously differentiable and the dimension is greater than or equal to 2, then the curve has the Lebesgue measure 0, and so the occupation measure cannot have a density. So the density of the local time only exists when the function f is not differentiable. It cannot exist for smooth function or continuously differentiable. So this is something that we only define for, let's say, irregular curves. And this is this opens maybe the gate to geometry of non-smooth curves. Maybe you have some ideas about differential geometry. Differential geometry uses especially the notion of derivative. But here, if you have derivative of the curve, you cannot have a local time. So it is something that is only used for, let's say, bad curves, irregular curves, non-smooth function. Okay. Maybe we will just solve these two small exercises. Like this. Okay. Now first, if we have a function from 0, 1 to actives, continuously differentiable, okay, then we will use for the first exercise. The following inequality. You have a continuously differentiable function, then you have this inequality. Right? It will be less or equal than some constant. It is the supremum of the derivative. And then this is something C. This is an inequality which is known for differentiable, continuously differentiable function. Okay. We can use to prove the result. So the idea is to fix an integer n. Okay. And so now we have the following partition. Okay. From 0, 1. We'll take 1 over n, 2 over n, and so n minus 1. And corresponding to this t1, tn, we will look to the curve. Let's say this is the curve. So we will have f of 0 of f of 1 over n, f of 2 over n, and so on. Okay. But since we have this inequality, okay, this means that if you take two consecutive times here, the corresponding value of t and s will have a distance smaller than this constant minus s. Okay? So the distance here between these two poles will be less than c over n. Okay? If here this is the norm, and r equals to r. Okay? F of j, for example, here, minus f j plus 1 n is less or equal than constant c times the difference which will be this n. So these distances are smaller than a constant divided. Okay. Next, the idea is to cover this curve by the following balls. That's all. Okay. The curve, let's say the curve is CF. CF is included, you can see here, in the union of these balls of center F, J, N, and with the radius C over. From 0 to. And so the big measure will be less or equal than the sum. Okay. The big measure of the curve less or equal than the sum of the measures of these balls, but all these balls have the same volume, which will be some constant multiplied by the radius to the power d. So what do we get? The sum from 0 to n, some constant, that's d, multiplied by the radius to the power d. But if we make the constant is the same, we can make the sum, we will have n plus 1 here, and this a constant c prime divided by n, let's say, we will have n plus 1 and here n to the power d, so it is of the type of the size of a constant divided by n to the power d minus 1. But this converges to 0. If t is greater or equal than 2. It does not happen if t is greater is equal to 1. Which means that the big measure of this curve is 0 if the dimension t is greater or equal than 2. So differentiable curves R2, R3, and so on cannot have local time. If we want to look for local time, we only have to consider non-differentiable curves. For the second smaller exercise, why a measure cannot have a density if the support has the base measure 0. If it had a density, mu is absolutely continuous with respect to the big measure. Okay, means as density. Then there exists a function. We will always have mu of any set B is the integral of D of the density of X measure with the density. But if we take here the support, just take D is which we suppose as the big measure 0, then from one side we have mu of t is 0, and from other side the integral over the support or the x and t. But since this is what? This is the measure. If you integrate over the support, you will find the full view of the whole space. We're going to integrate over the support. So what remains is the 0 measure. But the measure is supposed to be non-zero. Okay? If I recall, we can define this occupation measure for any curve, okay? And we want to discuss the existence of local time or not, which is the density. If the curve is smooth, it is continuously differentiable, and it lives in RD, D is the local time of curve. So it is proper to non-differentiable. Now, okay, we will move to local time of stochastic processes. It is the same definition, but the only thing that changed is now the following. Stochastic process is a family of random variables, but at the same time is a random curve, is a family of trajectories. What is stochastic process? For example, one-dimensional stochastic process means that at each time t, we have a random variable. So okay, we have a family of random variable and it's by time. And so, if for each experience we have like this corresponds to this one. This value here is xt of omega. time, the other hand, the variables are defined on the same probability space, omega and p. Okay. And so we have each time xt of small omega. And if we change, so this corresponds to the fixed small omega from the probability space. If we change this small omega, we have another trajectory. So stochastic process is a family of trajectory. It is a random trajectory or random function because it is a family of function indexed by this element from 1. So since we have a family of trajectories, to each one we can define the occupation measure and discuss the existence of the density. Right? So we have a random occupation measure. It is random because for each trajectory we have a measure. And how becomes the definition? If for almost every trajectory, for almost every trajectory we have a density, then we say that the whole process has a local time. Okay. And now the local time is, so it is random also. It is a density defined on RD, but it also depends on the trajectory. Okay. So for each trajectory we have a density. It is important to note the following why we apply this to stochastic processes. And the answer is that most of the well-known stochastic processes are non-smooth, have non-smooth curves. As we will see, the basic stochastic process, which is the Miller process, also doesn't have smooth curves. So it is appropriate to study their geometry using this concept of geometry.
Question. So we define this local time, so to say, pathwise for each fixed omega.
Yes,
So,
almost sure. Yeah.
Yes, but so in which cases it is somehow measurable with respect to it's a random object.
Yes, it's a random object. Okay, we will see the results that guarantee the existence.
So this is a task which should be solved.
Yes, of course.
It's a heavy task.
Yes, of course.
It is a heavy.
Yes, measurability could be a difficult task, but maybe we will not go so deep in this.
You will mention something. When you have a random element.
Yes. Now we have the following formula called by occupation formula, which also is a characterization of the local time. So the local time of an RD values of the process is characterized by the following formula. We have from one side the integral from 0 to 1 of p of x of t with respect to time, and from the other side we have an integral of RD p of x rho of x of t. So if it characterizes the local time, it means that if we have a function rho x that satisfies this equality for each positive or bounded measurable function phi, then that's the local time of the process. Okay? It's characterization of formula. And it is a useful formula as we will see just later. For the proof of this formula, it is first we begin by some elementary observation. If we take a Borel subset from ID, then of course mu of d is the integral of an indicator of d of x and dx. This is obvious, right? But from the other side here, mu of d, by definition, it is the go back. So see here that mu of t is the big measure of the times t such that xt belongs to t. So this is exactly so this is exactly the integral of the indicator t. This formula here is just another writing of the definition. Now, if we take a step function, which is a linear combination of indicators, then by linearity of integrals, we can take that the same formula holds. Okay? For step function, fine. And then by monotone convergence theorem, we can expand this last second formula to every positive and measurable. Okay. And if we have a bounded measurable function, then we can divide it as write it as a difference of two positive functions, and again the formula holds. And maybe we can make an interpretation of this formula. From one side, we have an integral of phi of x of t with respect to time t. And from the other side, we have an integral of phi of x, rho of x dx over r. It's like a change of variables formula. But, of course, if we have a local time, we don't have differentiability. The process with respect to time, but still we can write a change of variables formula. So when differentiability fails to exist, we with the local time can replace it. Okay. Now there is a second approach to define local time, which is based on the last occupation function. Again, we consider an RD value in the stochastic process, and we consider a positive function such that which has an integral equal to 1. It is a density, a probability density function on RD, and we define the following family of functions by the epsilon of x1 divided by epsilon of d, phi of x divided by epsilon. I think you are familiar with this kind of family of function since it is used in property of convolution. And we will use the this property in the following report. Now, suppose that the process X has a local time, which is a continuous and bounded density of the occupation measure. Suppose that we have a density of the occupation measure, which is continuous and bounded. Then, okay, almost surely we have, if we write the integral of the epsilon xt minus u, then using the occupation formula, this is exactly the integral of the epsilon of x minus u rho x dx. This is exactly an application of the occupation formula. But now, what is this integral here? This is exactly a convolution between rho and the epsilon at the But since this function rho is continuous and bounded, then the limit of this will be rho when epsilon tends to 0. There are some properties related to this family of functions. One of them is this one. But there are others. For example, if rho, the function rho, is uniformly continuous and bounded, then this convergence is also uniform in RT. If this function rho is LP RT, then this convergence holds in LP samples. So there are a lot strong results related to this family of functions. But the basic remark here is that we have something that converts to the local time. We have an integral of 3 epsilon xt minus u. The limit is rho. It means that we can get the local time by means of this approximation. We can define the local time in another way, using this kind of a family of functions. And this leads to the following definition. It's a more general definition than the first one. For HU and RD, if the limit of these integrals exists, in any sense, in LP sense, in L2, L1, or even almost surely, then the limit will be also called the local time. We have seen here that if we have a local time with some property, then we have this result, the limit is low. And now we take this as a definition, another definition. Okay? It is not obvious that the two definitions are the same, but this is more general definition. If we want to be very precise, we can say that this is the local time obtained by approximation. The other one is the local time obtained by as a density of the occupation measure. Even in literature, you find these sentences. To be precise, here we obtain the local time by approximation, by this kind of value of approximation. And if we use the other definition, we say that we obtain the local time by as a density of the occupation measure. And this, in this definition, we can use any family of function of this type. Any family of function that converge weakly to the delta zero. Okay. Now, we have a smaller property that also I want to clarify, is that if a measure has two different densities in RT, and that with respect to the big measure, and that both of these density are continuous at some point u, then they will coincide at this point. Okay, let's understand what's going on. A density of a measure is not something unique, because the density is simply a function so that the measure is the integral of this function. It's written by the integral of this function. You may take this same density and change it in some points, and still it is a density of the same measure. However, if we have a density which is continuous at some point, then any other density which is continuous at the same point will coincide with it. They will have the same value. So there is something like uniqueness of the value and the continuity condition. Okay. While I want to speak about this, because up to the moment, maybe what is local time exactly is still not clear. It is the density of the occupation. But let's try to understand what does it measure exactly. What does it give us? So suppose that the measure mu has a continuous density. So we have a continuous local time. So the measure of any set D will be the integral, right? It will be given by the integral of D of rho of x. Now, so suppose that row is continuous, even continuous at some point, maybe if you want to precise. Okay? So if we take as D a small ball centered at some point, ball center U with a radius psi r that will be taken to be very small. Okay. So what will we find here? We measure this ball will be equal to the integral of this ball of the density of x. But now if this function is continuous, and if we take epsilon very small, then what is the equivalent expression of this integral? Rho will be almost constant at this point, will be equal to rho of u, and what remains will be the measure of the lambda of the ball. If epsilon is very small. So what does it mean? Be careful here we use continuity. Here that continuity is so rho of u is like the measure, occupation measure of this ball divided by the Lebesgue measure of this ball, the volume of this ball. Okay. But for very small epsilon. How much time you spend in this small ball divided by the volume of the area or the Lebesgue measure of this ball. This ratio of time by volume. The density of the time with respect to the space of the volume. Okay? It's like the contrary of the speed of the derivative. The speed is like the derivative of the length by the time. But this is something like exactly the inverse. It's you take the ratio of the time spent in a small neighborhood, but divided by the measure of the sample. Okay? So like you have a curve like this. Of course, this is a smooth curve, but we have to imagine that it is not smooth. You take at some point u a small ball, and you see how much time spent in this ball, and you divide by the volume of this ball. If you take a very small ball, you will find as a limit the local time. Okay. But to have this interpretation of local time, we need some continuity. Okay. So when looking for local time, it is important, or it would be better to have a continuous version of local time, continuous density of the occupation. Okay. Now I will discuss some criteria how to prove the existence of the local time. Okay. I have chosen two efficient criteria. There are a lot of them. I have chosen two which are very efficient in application. Okay. So the first one discusses the case of a centered Gaussian process. So it does not work with any stochastic process. We only consider Gaussian processes. Okay, maybe I have to recall the definition of the Gaussian process briefly. I hope that everybody knows the Gaussian derivative. The Gaussian process so we say that xt is Gaussian if we take if for every d1 d2 every constant, the random variable or the random vector alpha 1 xt1 alpha n xtn is Gaussian. Of course, if it is RD value, if each x of t is an RD, this is an RD value stochastic process, then this is a Gaussian vector. And if this is just a real one-dimensional stochastic process, then this is a Gaussian vector. So it should be Gaussian every linear combination of a finite family of random variables from this process is a Gaussian. So Gaussian does not mean that each x of t is a Gaussian. No, it's more than that. It's given by every linear combination is a Gaussian. And we denote by B of S and T the covariance matrix of the vector. Of course, XS, XT is a Gaussian vector, definition, and we take its covariance function, B of ST, to a covariance matrix, and we define the following approximation of the I of epsilon is the integral of the epsilon d x of t minus 1. Okay, we choose the following specific family of approximation, which are derived from this Gaussian density exponent of minus the norm of x squared divided by 4. This choice, of course, it is explained by the fact that this family of function has good relation with Gaussian processes and Gaussian random variables and Gaussian random vectors. Okay, so the criteria is the following. If the following double integral from 0 to 1 of 1 over the square root of the determinant is finite, then the limit of this family of random variables exists in infinite sense. So we have a limit of this family of random variables, which means that we have a local time, according to the last definition.
The last definition, we considered all possible fields. And here
No.
only this
No.
particular family.
And
the
no,
epsilon.
here we just fix,
We fixed some.
yes, you
Okay.
fix anyone. You can
We
use
fix-
any family of
Yeah, field, yeah.
yeah. You can use any family
Yes.
and check the limit. If you get the limit, it is local.
Yes.
And
so
you can-
for different families, we cannot get different limits. Yeah.
But they are okay. But then you have to stick to this, to the family that you use.
Yeah, yeah. So
Okay.
this was my question. So,
Yes.
so the local time depends
On the family.
on field which you choose for the
Yes.
approximation.
Of course, yes. Yeah. And it is always called local time.
Yes. Okay, so we may have different local times for different fields.
It may be different. It may be different, and to be very precise, we always refer to the family of approximation that we use. So it is a local time, let's say, according to this family of
Yes.
approximation. Okay. So let's just understand why we have this criteria and why the finiteness of this integral gives us the existence of a limit. For this, we will use just the following criteria, which is a good technical result. Suppose that we have a Hilbert space. Okay? Hilbert space. Here it will be a two space. and we have a sequence of elements from this space. Of course, if we want to know if it converges or not, we may use Gaussian criteria. Okay? But there is another very smart criteria that we use a lot in studio. Okay. So the criteria is the following: xn is a limit of convergence in the space H if and only if yes, the following sequence we have the inner product xn xn. So it is a sequence but with two indices. Right? If this sequence has an element, but now of course this is a real value sequence. Okay? This is the inner product has element or converges. Okay?
As m and n tend to 0.
Yes, to infinity, yes, of course. Right. So, a good criteria, and the proof of it is not such complicated. Easy. So, we have the convergence of the sequence is equivalent to the convergence of this sequence. And in our case, we will apply this criteria because we have here a family of I epsilon, they are square integrable random variable. Okay? So they are elements from Hilbert space L2 space. And to, of course, the index here is epsilon, but we can generalize this. Okay? So we want to prove that I epsilon converges in L2. It is enough to check the inner product between I epsilon prime has a limit when epsilon and epsilon prime tends to 0. Of course, the inner product in L2 is given by the expectation of the product in L2 space. So, the following. So we compute expectation, which is of I alpha I b, which is the inner product, and the computation are not such difficult. We have expectation of okay. If we make the product of the two integrals I alpha I beta, we will have a double integral, but with different also variable s. Okay. And then, since the function inside the integral are positive, we can exchange the order of integration. The expectation is itself an integral, and we can put it inside. Okay. And now, here we have a function expectation of a product of function. So this product is at the end it is a function from x of s and x of t. So to compute the expectation, we need to know the distribution xs, xt. But since our process is Gaussian, then this x of s, x of t is a Gaussian vector. Okay? And this expectation will be exactly the integral over r to d product of these two functions, and then we have to put the density of the Gaussian vector. Here we use some property of Gaussian vectors. Okay? What is the density of the Gaussian vector? Okay? Of course, if we have an invertible covariance matrix, then we have a density. And we have the formula of this density. But remains easy. So we want to show that all these big integrals now converge when alpha and beta tends to 0. But we first make a change of variables, and this change of variables will lead to the integral of the following time. But here there are now alpha and beta in the first part, and the alpha and beta will be in the second part. And then what remains is to apply the various dominated convergence theorem. Of course, we have these two functions do not depend on alpha and beta, but all this term here, it depends on alpha and beta. It is exponent of minus something positive. It is dominated by 1. Okay. And of course, the condition on the covariance function that is given in the theorem ensures that this integral of the dominating function is integrated. So we have this result right here. It is simply, it is easy. We just need to compute the covariance function of xs xt, the covariance matrix, and just compute the integral and check if it is finite or not. Now we have a second criteria, which is given by the following integral. So again, x of t is an anti-value stochastic process, and we want to know when it has a local time or not. So if the following integral here is finite, then the process x has a square integration as a density of the occupation. And let us understand why it is so. Why does this condition imply the existence of this density? The reason is given by the following. There is a small result about densities of measure.
Can you show the statement? Then it has a square.
Yes. So how do you know that a measure has a density or not? Here is a question. Answer. You can use Fourier transform to the measure. If the Fourier transform of the measure is square integrate, then the measure has a density, and this density is also square integrate. It's like the inversion formula in the Fourier transform. So here, to prove the existence of local time, we need to prove that the Fourier transform of the measure mu is square integrate, which means that, of course, we don't have one single measure, we have a random measure, we have a family of measures. So we compute the expectation of the integral of the Fourier transform of the measure mu to the power. Okay, let's see how to compute this integral. Okay. Now, the Fourier transform of the measure is exactly given by this integral, the integral of the exponent of I, the complex number I, theta, inner product between theta and x, mu dx. And we take this integral in absolute value to power. Now how to compute this absolute value to power 2? We take the integral and we multiply it by its conjugate as shown here in the fourth line. But then we can put these two integrals together. Okay? One integral, it will be the double integral from 0,1 to 0,1, the exponent I theta x of t minus s of x plus. And now, what remains? So, now this is exactly the condition we have entered here. So this condition is equivalent to the square integrability of the Fourier transform of the measure. And this condition implies the existence of the density. This is the second criteria. And now let's discuss some examples. The first example would be the Brownian motion. Okay. I recall here the definition. It is a stochastic process, okay, with values in Rd, which starts from 0 at time 0, and such that for every t1, tn, from the unit interval 1, the random vectors, these increments, bt2 minus bt1, bt3 minus bt2, and so on, are independent, and each one of them always has the Gaussian distribution with mean value of 0 and covariance matrix X minus S of the alpha. And finally, the fourth condition is that the trajectories of this Brownian motion should be continuous, almost sure. And it happens that the multi-dimensional Brownian motion is in fact just a collection of D independent one-dimensional Brownian motion. So that its coordinates are independent one-dimensional Brownian motion. So now, here is the result that is related to the Brownian motion. Does it has a local time or not? So the result is the following. The d-dimensional Brownian motion has a local time if and only if the dimension is 1. It has not a local time in dimension greater or equal than 2. And the reason can be obtained by the first criteria that we defined. If we check, if we take B, of course, P of S and P of T, and compute the covariance matrix and compute this determinant, what we exactly find is the following. So this integral is 2 times the integral over delta 2. Delta 2 means that S is smaller than T of this function. Okay? Delta 2. Okay, we set this one. Okay. This is delta 2. Okay. 1/2 of the square 0 times 3. Okay. We can compute this integral. It's not difficult. We can make some change of variables here. S, T minus S. And we can compute it, and we can check that it only exists. It is only finite if dimension D, if this parameter D is equal to 1. This is a small exercise. Compute this integral and check that it is only finite in dimension.
But our criteria was not like if and only if. It was like if something finite, then we have a local
Yes.
time. That is, if something
Yes.
is not finite, we cannot.
Yes, we use in fact some other arguments, and we prove that the local time does not exist in the dimension greater or equal than 2. Okay.
In spite of the fact that trajectories are still not smooth.
Yes, but the local time does not exist.
Problem with Acrobat Reader.
same page as here, where I just had some trajectories of one-dimensional Brownian motion, okay, and one trajectory of a two-dimensional Brownian. Okay, just here, and then we discussed the local time of Brownian motion, and here I want to give a historical outline. The first results that were stated relative to the local time were in relation with the Wiener process of the Brownian motion. The first result was proved by Levy in 1940s when he considered in his paper the following function, ft of x, which counts this is a Lebesgue measure of times s from 0 to t, such that the Brownian motion with s is less or equal to x. Of course, this kind of function is not strange. You compute the Lebesgue measure of times s such that p of s is smaller than x. This is exactly the distribution function. This is the distribution function of the occupation measure. Of course, you may know that a measure has a density or not through its distribution function. If the distribution function is differentiable, then you have a density. And that's exactly what he proved. He proved that this function is almost surely differentiable with respect to the variable x, which means that the occupation measure of the Brownian motion, the one-dimensional Brownian motion, has a density. So the Brownian one-dimensional Brownian motion has a density. The second result was obtained by Trotter in 58, and he proved that this local time that was discovered by here we add another parameter t because he considers the interval 0t, while I just gave a definition with an interval 0, 1 for simplicity. But if we take the time from 0 to t, then we'll have a parameter t, and the dependence with respect to this parameter is a continuous dependence, as shown by the Trotter. So we have a version of the local time which is continuous with respect to both variables t and x. The third result was obtained in 65 in the book E2 and E15, where they proved that the following representation for the local time, which is a little bit similar to this one. The occupation measure of a small ball divided by the Lebesgue measure. Here, it is the local time is the limit when a tends to x, or a is greater than x, of the occupation measure of the interval x a up to time t divided by the length of this interval. Of course, then the theory was developed in many directions. You can say that a lot of people consider different stochastic processes and discussed the different criteria for the existence of the local time. Also, it was discussed condition to have continuity, for example, property of the local time. So this is what simply we do in this theory. We look for the local time of different processes and what are the properties of this. Does it exist or not? What are its properties? Continuity, regularity, representation, anything that we can find about local time. This is our job. Okay. Next, we'll consider a specific family of Gaussian processes introduced by Andrei Drogovtsky in 1998, and these Gaussian processes are called integrators if exists a constant C such that for any partition of the unit interval and every real numbers, we have the following inequality, where here expectation is sum squared, and from the other side we have C times the sum AK squared k plus 1. Okay, the definition may be a little bit tough to understand from the first sight, but as their name indicate, these processes are introduced to integrate, to be able to integrate function with respect to these processes. Okay, let's see this from this definition. If we denote by gamma the following very simple function, sum of ak tk plus 1, and then we can define the integral of this function with respect to x in a very simple way as a sum of ak x tk plus 1 minus x. Let's define the integral of this function with respect to x and this one. Then, according to the definition, the definition tells us that the expectation of this integral of 2 is less or equal than c times the integral of gamma squared. Of course, this sum here is exactly the integral of gamma squared. Okay? See that the gamma is sum of ak and plus 1.
Return to the definition.
Yeah.
So any partition and any real numbers.
Yes, and you have a universal constant. So the definition is introduced in such a way that we can define this integral. Okay. For this specific or the very simple step function, and this integral satisfies this property, but then we can extend it to all square integrable functions as follows. Using density of step function in 2 till 1, now we can define the integral of f of t dxt for every f in L2. Since we have some property here, we can define the integral of a step function, and using this inequality, we can extend this definition to all square integrable. Okay, maybe one should ask a question, why we define stochastic integrals? And why are they important? The stochastic integration is like the other side of a stochastic differential equation. If you have a, what is a stochastic differential equation? It is an ordinary differential equation for which you add a random noise, a random perturbation. Then it becomes a stochastic differential equation. But if you want to give an integral formulation, then you need to define stochastic integrals. And here, the definition allows us to integrate with respect to this wide class of Gaussian processes. And the integral obtained has the following properties: that the integral of any square integrable function is a centered Gaussian random variable, and this is exactly the variance of this integral. It is less or equal than c times the normal of n squared. See that in stochastic integration we integrate which is things what are square integrated, not integrated. Okay. We can prove also, okay, maybe from definition we can check that the following inequality holds. The expectation of xt minus xs squared is less than this constant c times t minus s. This is from the definition. We take just the indicator of st. But then this property can be used to prove that integrators have continuous version. We may use the Kolmogorov continuity theorem. And since we have Gaussian random variables, this inequality helps us to prove the existence of continuous version. Some examples of Gaussian integrators. First is the Brownian motion itself. And also here, this process is called the Brownian bridge, Bt minus T1, called Brownian bridge. Because it always starts from, at time 0 it starts from 0. At time 1 you can check that when t is equal to 1 it is also equal to 0. So it is like a bridge between these 2 points. It is, we can check by the definition that it is also an integrator. And I added another example, which is the fractional Brownian motion with the Hertz index. So what is the fractional Brownian motion? It is a central Gaussian process with the following covariance. Maybe I should recall that. Gaussian process, the distribution of Gaussian process is uniquely defined by the mean function, the expectation, and the covariance function. So if you know both of these two functions, then you know the distribution of the Gaussian process. So we have a covariance like this, but we can check that if this first parameter alpha is smaller than 100, then expectation Bt alpha is alpha squared. We can compute it since we have the covariance of any Bs and any Bt. Divided by the absolute value of t minus s will tend to infinity when t minus s tends to 0. It cannot be an integrator since this property here will contradict the following that we have always that expectation xt minus x s squared is less than some constant times t minus s. But here the ratio of these two expressions tends to consequence, so cannot be integrated. We use other characterization to prove that in the case alpha greater or equal than 1/2, it is in fact integrated. The following representation is very important when dealing with Gaussian integrators. The central Gaussian process, which starts from 0, is an integrator if and only if there exists Brownian motion B and a continuous linear operator in L2 of 0, 1, such that xt is the following given by the following entity. So a Gaussian integrator is can be simply defined by an operator. Give me an operator from L2 of 0, 1, I give you an integrator. It's simply expressed by this integral of this function with respect to the Brownian motion. Of course, the integral with respect to the Brownian motion is a specific case of the integral defined with respect to integrators, and it is even defined even before the introduction of integrators. Okay. So what we will do is, okay, we introduce this new family of stochastic process, and we will see do they have local time or not. Maybe just before going to the local time, some examples. If we take a specific linear operator, what we could have as what can we produce as an integrator? If we take A as an isometry of 0, 1, then we can check that the obtained integrator is a linear process, a Brownian motion. And if we take the operator A as the identity minus the orthogonal projection on the linear span of indicator of 0, 1, indicator of 0, 1 is just a function, an element of 0, 1, and we make orthogonal projection to the line in the square. Then the result is a Brownian bridge. So we can understand, or we can guess what is the operator that corresponds to each integrator. Most of the cases we may know this operator. Now we fix a Gaussian integrator x by the following representation, and our result here was to prove when it has local time. So if the operator A is invertible, then the Gaussian integrator x has a local time given by the limit of this approximation. Again, these p epsilon 1 are these Gaussian density that I defined in this lecture. And we can prove the existence of this L2 limit using the criteria number 1. Okay, the proof is not such long, since...
Come back, please.
Okay.
Just
It is enough to, okay, if you want to use the criteria number 1 to compute the covariance matrix of x of s, x of t, and try to see, compute its determinant, and see the integral of 1 over square root. This is the criteria. So we can check that the variance of xt minus xs is exactly given by the norm to the power 2 a and applied to the indicator s. Okay, maybe here we used the second criteria, which finds the local time as a density of the occupation measure. It also works, okay? Since what is the expectation of exponent I theta xt minus xs, since we have the variance of this xt minus xs, this is exactly the characteristic function of the random variable xt minus xs. And since it is Gaussian, then the characteristic function is given by this formula. And now, if we integrate this with respect to theta, what we find is exactly a constant divided by this value here, the norm of a and theta st. And that's it. How to prove that this is a finite integral? Then we use the inequality since a is invertible, then if we have a of x or a of y is always greater than some constant, which is given by 1 over the norm of a plus 1. We have this lower bound of a phi if a is invertible. Of course, continuity of a tells us that this is less or equal than some constant, the norm of a. But the invertibility will give us the inequality. If we use this here, then this integral will be less or equal, then we can get rid of the operator a, and what remains is the integral of 1 over square root of t minus s. One can check that this is commutative. So, I think it is not such difficult to try to compute these integrals. There are some Gaussian properties, Gaussian density of Gaussian on the variables, and even the integrals are known formulas. So here we show that this Gaussian integrator is always a local. But this is in the case of an vertical operator. I will leave this small exercise to you. Prove that the Brownian bridge has also square integrable local time, even though the associated process, the operator is not there. Of course, we have here the definition of the Brownian bridge. Move back. The Brownian bridge is defined by Bt minus Tb1. And you have two criteria. Try to use one of them to check that this process has a local time, even though the associated operator, is somewhere here. It is identity minus p. This is not a vertical operator, of course. Okay, thank you very much.
Maybe someone has a question? Okay, if no, then
Discuss Friday.
yes, so here you see you have some exercises, so you can try to solve them. And if you will have some problems or some additional questions, please come tomorrow, for example, before lecture, and or between lectures, so we can answer your questions. So please try to read once more your notes, and maybe we can somehow share slides with you.
Yeah.
So maybe you can help me, because I'm not sure how to do it, how to share all.
Put everything on the web page.
I don't know where is the web page, so.